So I'm studying electromagnetic waves, and it's a spectrum. And we'll get into why they're called electromagnetic waves in a second here. As you can see, as you go from left to right, the waves become more intense, and we kind of broke it down into different segments. And these electromagnetic waves, travel at the speed of light, and they can also travel through objects and even the vacuum of space. And once you look at the frequencies, sorry for the pause there, you can see it goes from the least amount of frequency, which is radio, up to microwaves, to infrared, to the visible light or visible waves, which is our light, which gives us our colors, and that's a small section that of the electromagnetic spectrum that we could see with our own eyes, and that's what gives us our colors. And then there's ultraviolet, gamma ray, or X-ray, and then gamma ray. Going from the left has the lowest energy, or EV, and going to the right has a higher energy level. Same with frequency that's measured in hertz. Okay, so what we have here is the graph for wavelengths. So up here, up and down, is the amperage, and that's represented by A, and wavelength is represented by that symbol there. It's kind of clearly drawn, but it's pretty accurate. And these little notches here represent distance over time. And I'll show you, it sits on the x-axis, and I'll show you how the waves work using these measurements. So the red line represents the wavelength. And as you can see, the notches, it's kind of clearly drawn, but best I could do, goes up all the way 1, 2, 3, 4, 5, 6, 7, 8. It's 8 amps. So it goes up to 8, and it comes back down to 0. And it inversely goes down the exact same 8 notches, and then back to 0. It just kind of does that over and over again. That is the amplitude. The amount of notches that it goes up is the amplitude. The wavelength is the length of the wave. So as you can see, from one section, one cycle, we'll call it for now, is when it goes up and then back down and meets. So that would be one cycle. And that is 1, 2, 3, 4, 5, 6, 7, 8. 8 notches of the wavelength represent W. So these notches could be any value. It could be for size or the energy. But it represents size. Still learning. Whenever there's an electric wave, there's also, in correspondence, a magnetic wave. And as you can see, it matches the exact amplitude and wavelength, excuse me, as the electric wave. However, it's on the y-axis instead of the x. So it's the complete polar opposite position in space, but they all converge at these converging points, just going opposite directions. I said before, the wavelength and the amps are equal on both the electric and the magnetic fields, or wavelengths. Here is a electric wave going on the x-axis, as you can see, as it goes farther away. This is in 3D, 3 dimensions, best I could do. As you can see, it's the same amplitude and frequency. So the y-axis going left to right, and x-axis going back and forth, going two opposite directions, two different planes. As you can see, they both have the same amplitude and frequency. They both match each other. So as we look at the wavelength, electric magnetic wavelength, the light spectrum is, a very small portion of this wavelength that our eyes could actually see, and that gives us our colors. And it goes from the highest point of the wavelength, which gives us our purples, to the lowest, which gives us our reds. And eventually when it gets so low, it becomes obviously to the point to where you can't see it anymore. And at that point it's infrared. And on the opposite side, when it gets so high, once wavelengths get so high, you can no longer see it, and that's ultraviolet rays. So a wavelength, or a wave, I should say, is a disturbance in which carries energy from one place to another. So it's how energy travels throughout the universe. And I got the speed of light right here, represented by c, is 3 times 10 to the 8th power meters per second. And amps is represented by A, and wavelength is represented by that symbol there. Now a period is the time for a wave to complete a cycle. So a cycle is just when the wave goes up and down and meets back at the center point. And the frequency is how many cycles can occur in 1 second. And just like talked about earlier, the frequency is measured in hertz, which is how many times a wavelength does 1 cycle in 1 second. Microwaves are very small, starting at 10 to the 9th power all the way to 10 to the 11th power per second, hertz. Infrared is 10 to the 11th power to 10 to the 14th. Visible light is 4 times 10 to the 14th power to 7 times 10 to the 14th power in hertz. Ultraviolet is between 10 to the 14th power and 10 to the 17th power in hertz. X-rays is 10 to the 17th power to 10 to the 19th power. And gamma rays is 10 to the 19th power onward. This is Planck's constant. This will be important to remember later. It's the measurement that describes the relationship between a photon and its frequency, or the energy of a photon, I should say. And Planck's constant is symbolized by the letter H, and the value is 6.626 times 10 to the negative 34th power. And this is a joule, another unit of measurement for energy, represented by J. It measures the amount of work done when the force of 1 Newton moves an object 1 meter. So I'm going to learn an equation to convert electromagnetic waves into joules, so I could understand how much energy it produces. So the equation is E equals Planck's constant times the speed of light divided by the wavelength. In this case, it's gamma, and I got the numbers down there. Planck's constant being 6.626 times 10 by the negative 34. Speed of light represented by c, and wavelength by that symbol. So I wrote down the equation as so and punched it into my scientific calculator. Planck's constant is measured in joules per second times the speed of light, which is the 3.0 times 10 to the 8th power, and then divided by the wavelength. In this case, it's gamma rays. Now the equation we did is gives us the answer of 1.98 times 10 to the negative 25 power of joules per second. And that's the energy each photon has, so that's per photon. So Halloween is upon us, and spent time during the night with Tyler. Wasn't sure what we wanted to do. So I think we should go somewhere, like not in a populated area, and just get a cabin somewhere.
Well, have you ever seen Cabin in the Woods?
No, I haven't.
Well, watch that and then you'll realize why I don't want to do that. Camp out in my backyard or something.
In your backyard?
Yeah.
That ain't scary.
It's spooky scary.
So we decided to spend time at a park, and it turned out to be a park that I went to a few times as a kid, and got real nostalgic about it. A lot of memories here, and it's really cool to revisit it. It hasn't changed one bit. This was the playground that I grew up playing on. I went here a few times. This place was amazing because there's like a whole jungle gym out here. Steps, dude, as a kid. You come down here and play. Pretend this was a fortress. I had to crouch, and it's like I'm going through an air vent. But I used to play in here all the time as a kid. I play here all the time.
A lot of wood.
There's a lot of wood. Used to play down there. Yeah, that's what I mean. This is where I hung out.
Ow, man. I didn't need one.
Yeah. Smooth.
Yeah.
Dude, I remember we played hide and seek or tag, and you'd see each tower here. That'd be like our base, and we'd like choose a base to start at, and then we'd try to get each other. I only came here probably like 3 or 4 times in my childhood, but they're always really great memories. Pit, there was only spiders down here, and it creeped us out. We never went over here. It's actually a night just like this where me and my stepdad and my mom took me here. And he was a big guy, still is, but I'm a lot bigger now. But I was probably like 7 or 8, and he took me here, and we're playing tag and hide and seek and stuff, and I was running through everything. It's a lot of fun. Good memories. That was a fun night, and going back to my studies, learning about different types of energy. Now I'm learning about thermal energy, which is basically heat and temperature. Heat is the transfer of thermal energy between objects with different temperatures, and temperature measures kinetic energy of particles within the object. Thermal energy is created by the motion of molecules and atoms. The faster the molecules move, the hotter it is. So heat transfers energy from a hotter one to a cooler one. So I'm going to learn the formula of heat and how heat is created. and how it transfers and all that. So that's going to be a lot of fun. This is a diagram as heat kind of disperses and gets cooler. At the center there, it's white, which is the hottest, and it turns into yellow and then orange and red and then purple as it gets cooler. As you can see, it's kind of a radius around the hot object, and it gets cooler as it goes further away from that object. Kind of shows how the heat in the air is, or the heat from the object heats up the air and transfers that heat to the air. And you can see the heat diminishes as it goes further away from the heat source. So I did a little demonstration. It's a drawing of like a hot coal in the center there, and the heat will radiate from the hot object into the object that it's sitting on, starting at yellow at its hottest, and it phases into orange to red into purple as it cools off. This represents the energy, thermal energy, or heat being transferred from one object to another and how it spreads out. Here's the same thing with a crude drawing of a ice cube sitting on a surface. The coldness of the ice cube cools off the temperature of the surface it's sitting on. The brighter the blue, the colder it is, and as it goes away from the ice cube, it starts getting warmer and warmer. So temperature is measured in either Fahrenheit and Celsius, and here's the equation to determine or how to convert Fahrenheit to Celsius. So let's say it's 70 degrees. First, you subtract 70, or the temperature in Fahrenheit, by 32, which you get 38. Then multiply that by 5, which turns out to be 190. Then divide 190 by 9, and you get 21.1. So 70 degrees Fahrenheit equals 21.1 Celsius. And if you were to convert Celsius to Fahrenheit, and say you got 10 degrees Celsius, first multiply the Celsius by 9, so 10 times 9, which is 90. Divide it by 5, so 90 divided by 5 is 18. And then add 32. 18 plus 32 equals 50. So 10 degrees Celsius equals to 50 degrees Fahrenheit. So this is heat capacity, and the specific heat capacity is the amount of energy in joules needed to raise the temperature of 1 cubic gram by 1 Celsius. And on the left there is the heat capacity of a few things. You got air, which is 1,000 joules per kilogram. Water, it's supposed to be 4.184, not 4,184. It's 4.184 joules per kilogram. So we have a problem here to solve. As mentioned before, water's heat capacity is 4.184 joules. And the problem is how much energy is required to heat 40 kilograms of water from 35 degrees Celsius to 50 degrees Celsius. So we got the mass, which is 40 kilograms, the heat capacity, which is 4.184, represented by C, and delta T, which is the amount of temperature gained. So it's 50 minus 35 equals 15, so it gained 15 degrees going from 35 degrees Celsius to 50. So to solve the problem, we got the mass, which is 40 times the temperature change, which is 15 degrees, times the heat capacity of the material, which in this case it's water, which is 4.184, and that equals to 2,510 joules. So if you want to heat up water from 35 degrees Celsius to 50 degrees Celsius, it's 40 kilograms of water. It would require 2,510 joules. So here's a different equation. We're trying to find the heat capacity of this object based on the information given. So it takes 120 joules to heat up this unknown object of 20 kilograms, not grams, from 15 degrees Celsius to 35 degrees Celsius. We have Q, which is the amount of joules, 120, the mass, 20 kilograms, and delta T, which is the temperature change, going from 15 degrees Celsius to 35, so it's 35 minus 15, giving us 20. And we're going to look for the heat capacity. So it's mass, 20 kilograms, times 20, the temperature change, and it equals 400. And to find the heat capacity, you divide 400 by the joules. 120 divided by 400, So 120 divided by 400 gives us C equals 0.3 joules per kilogram Celsius. And that's the heat capacity of that material. So now moving on to the study of electricity and how it works. It works on the atomic level, and this is the Bohr's model. And this represents inside of an atom. It's the nucleus of an atom. And in the nucleus, there is protons, neutrons, and electrons. The protons are represented by the red, the neutrons are the blue. The electrons sort of orbit the nucleus that are made up from the protons and neutrons. They orbit the nucleus the same way that the moon orbits the Earth, or the Earth orbits the sun. And the number of protons in the nucleus of an atom determines what element it is. And this is represented by the atomic number on the elemental chart. For example, if it has 29 protons, that's a copper atom. However, the number of electrons and neutrons does not affect the element. Now, an atom could be either positively or negatively charged. What determines that is the ratio between protons and electrons. Electrons give off a negative charge as opposed to the proton that gives off a positive charge. And it works as kind of a balancing scale. If there are more protons than there are electrons, the atom is positively charged. And if there's more electrons than protons, the atom is negatively charged. If the number of protons is the same as the number of electrons, that means the atom is at its neutral state, or they call it the ground state. So if you have a nucleus of an atom that has 5 protons but 3 electrons, since there's 2 more protons than electrons, and protons represent a positive charge, that atom will be or have the positive charge of 2. Or if there is 5 protons and 7 electrons, there would be 2 more electrons than protons, so the atom would have a negative charge of 2. There are different layers of orbits called shells that determine how many electrons could be on each orbit. Orbit closest to the nucleus, the protons and the neutrons, is the K shell. And each shell could hold a certain number of electrons. So the K shell could hold 2, then the next layer is 8, then 18, then 32, then 50, and then 72. So it could hold up to 6 layers. A positive or a negative charged atom is called an ion. As to where atom with equal parts proton and electron is just a neutral atom, or just an atom. Now the electron is actually much, much smaller than the proton and neutron, giving it a lot of room to be able to move. And the movement of electrons is actually what creates electricity. A little bit of a typo, but that's okay. So electrons can move from the outermost shell and be pushed out of their orbit to another atom. And what determines this is atoms always trying to find their neutral state. So on the left, you can see the nucleus has 2 protons and 9 electrons. That gives it a -7 charge, meaning there's 7 more electrons than protons. And since the electrons have a negative charge, that gives it a negative charge since there's more electrons. And vice versa with the positive ion on the right. There's 5 protons and only 3 electrons, giving it a positive charge of 2. So the ion on the left will transfer electrons to the ion on the right till the number of electrons match the number of the protons. And this creates a current, which is what electricity is. So that is how electricity is formed. Now we're going to be learning about amps and volts and ohms, the unit in which measures the electricity, as well as watts. This was a lot of fun learning. First, we'll do voltage, which is the flow of free electrons between atoms. It's the electrical potential difference between 2 points when 1 joule of energy is transferred. The difference between the negative charged ion and the positive charged ion is what determines the strength of the voltage. So on a battery, you have negative and the positive terminal, and the negative ions lose their electrons and they move all the way over to the positive ions on the other side, which creates an electric current. You could also pause this video at any time to read what I got down. Ions seek the ground state. So an ion with a +4 charge contacts an ion of one with -2 charge with 4 protons. The positive ion with 4 protons and 2 electrons will give up 2 more electrons. So the ion will have 4 protons and 4 electrons, which neutralizes the atom, making it a neutral atom of no charge. And it's the exchanging of these electrons that create the current or electricity. Current is the measurement of the flow of electrons at a certain point. Now, amperage is the electrical charge that is flowing through a system or maximum amount of electrical current a system is capable of handling. 1 amp is equivalent to 6.241 times 1018th power, I believe, electrons per second. Now, constant potential difference is pretty important. Steady voltage maintained between 2 points of a circuit voltage remains the same over time, giving it a constant push. And ohms is a measurement between 2 points of a conductor when a constant potential difference of 1 volt is applied to these points and a current of 1 amp is produced. It is the equivalent of 1 volt per 1 amp. So this is the formula for volts, watts, and amps. Voltage represented by the V. Watts is power, measured in power for watts or P. And amps is measured in current, which is represented by I. If you want to know the power of something or the watts, it's current times the volts. If you're looking for the amps, it's power divided by the volts. And if you're looking for the voltage, it's watts divided by the amps, or power divided by current. So if you wanted to find the power of 5 volts and 3 amps, it's 5 times 3, and it's 15 watts of power. If you want to know the volts of 20 watts and 5 amps, it's 20 watts divided by 5 amps, which is 4 volts. And if you're looking for amps, and you got 12 watts and 3 volts, it's just 12 divided by 3, which is 4. So 12 watts divided by 3 volts is 4 amps. And 1 watt is the same as 1 joule. Joule per second in heat. So if it's 1 watt of power, in 10 seconds it would be 10 joules of heat that was produced. Like in the electromagnetism section, where we discussed the energy of joules, we could kind of combine our knowledge that we learned on the electromagnetic spectrum with joules with the electricity and the heating. So I came up with a little problem of my own. So electricity converted into heat using joules. We'll first have to determine the watts, which is 1 joule per second. So if we have 12 volts and 3 amps, the formula is power, which is measured in watts, is equal to the current and the voltage, or the amps and the volts. So 12 volts times 3 amps, 12 times 3 is 36, so it'd be 36 watts. So, and it'll be 36 joules per second. Now, from what we understand about electromagnetism section, we would need the heat capacity of the material that it's going to, the joules of energy. I use copper, which is 0.385 joules per gram Celsius. And I chose the mass of 0.5 grams. So if 36 joules were to go into a half a gram of copper, the formula would be 36 divided by the heat capacity of 0.385, the heat capacity of copper, divided by 0.5 grams. And for whatever reason, I wrote down a totally different equation, which was 20, down below. Don't know why, but it's meant to be 36, so I'll give you the correct answer. So 36 divided by 0.385 divided by 0.5 is 187 degrees Celsius, or 368 degrees Fahrenheit. Just for whatever reason, I wrote down 20 instead of 36, but just replace the 20 with 36 and the answer is correct. So I didn't make an error on this one, so it'll be less confusing. Here's another problem. This time it's 8 volts and 3 amps to determine the amount of power or watts. So 8 times 3 equals 24 watts, which equals to 24 joules per second. It'll be applied to 1 foot of copper wire, which is about 15 grams roughly, give or take, but we decided to go with 15. So 24 watts divided by 15 divided by the heat capacity of copper, which is 0.385, and you get 4.15 degrees Celsius per second, or 7.48 degrees Fahrenheit per second. As you can see, it's much smaller because the mass of the material is much larger. Now it's time we talk about magnetism, the second part of electricity. You could pause it at any time if you want to read it, or if I'm going too fast. Moving charges create magnetic fields. Changing magnetic fields can induce electric currents. They are inseparable and directly influence each other. Magnetic fields can be observed by the force they exert on moving electric charges or other magnetic material. Every magnet has a north and south pole. When opposite poles face each other, the magnetic fields align, creating a pulling force. When the poles face each other, the magnetic field lines try to push apart, causing repulsion. Electron alignment in magnetic materials or metals have electrons spin in a predominantly similar direction, creating a magnetic field. Electrons in metals temporarily align themselves with the magnetic field of the magnet, creating a magnetic attraction. Within a magnetic material, small regions called domains have aligned electrons, and when a magnet is near these domains, they could align with the magnets and the magnetic field, causing attraction. Now I've been studying about astronomy and trying to understand what we know so far about the origins of the universe and the Big Bang. About 13.8 billion years ago, the universe was a singularity, a very, very dense point in space where all matter and energy was condensed into a single point. Eventually it started to rapidly expand, propelling gases outward in all directions from the point of origin. During inflation period, the universe expanded at an exceptionally high rate. Space itself expanded at a rate faster than the speed of light. Due to the laws of motion, the universe is still expanding, but much slower now. After the Big Bang, the universe was very, very hot and dense, filled with fundamental particles such as quarks and electrons. As the universe rapidly expanded and cooled, quarks combined to make protons and neutrons. After the universe cooled, protons and neutrons collided, creating the nuclei of the atom, mostly helium atoms and hydrogen. It took hundreds of thousands of years for electrons to settle around these nuclei to form neutral atoms, as we've previously discussed on the electricity segment. As the universe was still too hot to be captured, a long period of time the atoms of helium, hydrogen, and other light gases formed, and they formed in large clusters of gas, which became nebulas. As much time passed, the universe got cooler, as well as the gravitational forces of these gases being pulled together to form the first stars, where heavier elements like carbon, oxygen, and iron were created, and more, through nuclear fusion process inside of the stars. Hydrogen nuclei in stars, due to extreme heat and pressure, collide and fuse together to make helium, releasing energy in the process. The energy released from this fusion is what sustains its star's light and heat. It took about 380,000 years after the Big Bang for the universe to cool down enough to form atoms. Main sequence stars are stars that actively undergo hydrogen fusion into helium, are considered main sequence stars. Stellar nucleosynthesis. As stars evolve, they can fuse heavier elements beyond helium, creating a variety of elements. When a star runs out of hydrogen fuel, its core contracts and heats up, potentially triggering fusion of even heavier elements until it eventually collapses and dies, sometimes an explosion called a supernova. The supernova of a star released heavier elements such as carbon, oxygen, nitrogen, iron, and others, creating the building blocks of matter. Through the process of gravity and the force of gravity pulling these nebulas together to create stars, stars began emerging. becoming massive. And due to its mass, it has a very high amount of gravity. And it's these gravitational fields that create the orbits. Space rocks, things like that, could be caught in the orbit or the gravity of a sun or a star. Due to Isaac Newton's law of motion, it maintains its forward trajectory in the direction it's going and is being bent towards the sun, but never colliding into it, creating an orbit. The larger the star, the greater the gravitational fields are, which means it could affect matter from further distances away and have larger orbits. I'll go more into that later on a different episode when I study more on gravity, but that's kind of the basics. Once the building blocks of matter are in different atoms and elements that came from the furnaces of stars that exploded and went supernova, gave the building blocks to create other matter. We'll go over this in the chemistry section, but these elements bonded together to make different compounds, such as rocks, asteroids, using carbon and iron. And as it gained more and more mass, it gained more and more gravity. Planets form when small particles of matter and gas come together from gravity within a spinning disk. This disk is left over from the star's formation. This process is called, and please correct me if I'm saying this wrong, accretion. When it comes to our planet, during the formation of the Earth, intense heat generated by collision of large planetary debris, which released a tremendous amount of kinetic energy that turned into heat, as well as the formation of the core created heat by releasing gravitational energy as heavier metals and materials sank inward. Gases that gets pulled in by the planet becomes the planet's atmosphere. Early Earth's atmosphere was very thick of methane and carbon dioxide, which trapped heat from the young sun. The Earth was extremely hot, estimated to be around 3,608 degrees Fahrenheit, which kept the planet in a molten state. With the heat of the Earth and the toxic gas of the atmosphere, it made life impossible at the time, which I know isn't really a shocker. And that was the end of my studies. I've been working on this video for quite some time now, but if you made it through all this, thanks for watching. That's a lot, and it's probably pretty boring, but I just felt like kind of telling you everything that I learned. And a while back, there was a solar eclipse, and I was really excited to do that, to film it and show you guys. So enjoy the eclipse. It was really cool. The sky got significantly darker. I think it was about 70% coverage, and it's really cool to experience. So thanks again for watching, and enjoy the eclipse.